works for you. Now, make sure you find a system that works, or you're going to get 50 all the time. Oh, well, it could be worse than that. I've seen students work out a system that gives them the wrong answer every time, which is worse than guessing, because it's either R or S. You get a 50-50 chance if you guess, but many students sometimes develop a system that consistently gives the wrong answer.
I still don't see how having them work away from those are less. Like, by making it go clockwise, making it go counterclockwise.
Well, if you look at it like this, okay, the chlorine is number 1, the ethyl group is number 2, and this is number 3. So is this clockwise or counterclockwise? 1, 2, 3. Counterclockwise, right? But if you were to look at it like this, now see when you're not looking at a 3-dimensional object, everything is kind of confused as to where it's pointing. You see now 1, 2, 3 is clockwise, so you get the wrong answer. You have to have the right perspective. That's critical. Now, there's another trick you can employ, which is based on the fact that if you have an object like this that's asymmetric, and you switch any 2 groups, you generate the mirror image. Because if you stand in front of a mirror, your head doesn't go down to your feet. It switches from left to right. So if you pick a horizontal plane, if you will, if I switch for 3 and 4, that's the mirror image. If I switch 1 and 2, it's called transposing, that creates the mirror image. Now, this could be a little dangerous if you don't play the game correctly. So don't use it unless you're kind of desperate, it's your last option. You can make number 4 be the group furthest away from you anytime you want. The group furthest away right now is which number?
2.
2. I want 2 to be 4. So I take this 4 and put it where the 2 is, and take the 2 and put it where the 4 is. Since you're now looking at it correctly, you can just follow the numbers on the board. So is that clockwise or counterclockwise? Or was it R or S? No. Why? What did I just do when I switched those 2 groups? I created the mirror image. That's not what I started with. The mirror image is R. So what's the original? S. Right? As long as you know what you're doing, you know, lay down the breadcrumbs so you know where you've been, you can come up with the right answer. But don't use this casually. Right? If you're half asleep and only catching half of what I'm saying, don't use it. If you see it clearly, it's actually a very handy tool. Okay? And some people get very sophisticated with it and realize that if you switch 2 groups, you create the mirror image. If you switch another pair of groups, you go back to the original. So I could just say, well, let me switch 1 and 3. Now I'm back to the correct mirror image, and you can see now that that's counterclockwise. Yes. Always comes out right, as long as you know what you're doing.
So if you change this position with the arrangement number, it'll eventually get to a more, I guess, visually acceptable sort of.
Well, you never need to do more than 1 to get the smallest group away from you. But if you're only doing 1 switch, understand that you've created the mirror image. So when you read that, which you can do just by looking at the 1, 2, 3, That's wrong. That's the wrong answer, it's the other one. Now, the ideal is to just see it and read it in 3 dimensions, and sometimes you'll be lucky and the number 4 group will be away from you. But again, don't torture yourself with this, because assigning R and S is not a big deal. You have to do it because you have to have some way of talking about which mirror image you're talking about. The term that describes this mirror image relationship, where the 2 mirror images are not the same, that relationship is that of enantiomers. So those 2 stereoisomers that are not, we say non-superimposable, means you can't fit one inside the other exactly. Non-superimposable mirror image stereoisomers are enantiomers. Enantiomers are the most subtle form of isomerism because it's not always there. It's completely absent, the difference between the 2, in a symmetric setting. It only shows up in an asymmetric setting. Now, unfortunately, a lot of the reactions that we use to produce compounds create chiral centers in pairs, like pairs of shoes. You remember the free radical bromination. If you brominate butane, one of the products is 2-bromo, or chlorinate 2-chlorobutane. That will actually give you, statistically, a perfectly equal distribution of the 2R and the 2S. It's an uncontrolled process because the key step is the formation of this planar radical. Now, I'm showing the unpaired electron in the top lobe, but it really lives in both lobes. That is symmetrical, like a 3-bladed fan, the blades, or propeller. So the next step is a reaction with chlorine, which is basically also a symmetrical molecule. So you have random collisions going on, and as the chlorine comes in, let's define this face right here as the top face. So we've got this triangle, and there's a top side and a bottom side. The chlorine comes in from one of the faces because it's wide open, and it needs to get at that unpaired electron. If it comes in from the top face, is that any different from it coming in and colliding from the bottom face? If you're a chlorine? No. This is a symmetrical situation. Why would the chlorine even see any difference? Now, you can actually see a difference between the top face and the bottom face. In fact, if I put numbers on these, I'll use the same priority numbers, 4, 3, and 2. If you look from the top and go 2, 3, 4, is that clockwise or counterclockwise? Do it again from the bottom. Let's say you're looking up at the bottom of this. If you're laying down on the floor, looking up at the bottom of this, and you go 2, 3, 4, it's the same thing as I was doing before. This is clockwise to me, it's counterclockwise to you. chlorine could see that, like you can, then the chlorine would probably not react with the two faces at the same rate. Over the zillions of collisions, the chlorine doesn't care whether it collides top or bottom. You just get a zillion pair of shoes, basically. When the chlorine comes in from the top face, these three groups will go down. So the top attack creates one asymmetric carbon, or chiral carbon. The bottom attack creates the mirror image. So they come in pairs, and just like flipping a coin 10 million times, half the time it's heads, half the time it's tails. So you get an equimolar mixture of the two, which is called a racemic mix. A racemic mix is 50-50 R and S. The two enantiomers in exact equimolar proportions, exactly the same number of molecules of the two. So this is a reaction where you're actually creating chiral molecules, but you're unable to create one faster than the other mirror image, and you end up with a racemic mix. Now the problem with this is that this is an example of most of the reactions that we use. Even if a chiral carbon is being created, there's no control so that you produce one enantiomer faster than the other. If you look at this, though, it could be controlled. If I had a molecule coming in to react with this that had some asymmetry to it, like your vision, it would see the top face as different from the bottom face. Now your body has a huge army of these kinds of molecules that are chiral. So in a biological system, this kind of reaction can lead to one mirror image being produced at the total exclusion of the other. 100% R or 100% S and 0 of the other. Your body does that all the time because it's loaded with chiral molecules like proteins, carbohydrates, nucleic acids. They're all chiral. In the laboratory, not so much. We're really bad at mimicking biological chemistry from a stereochemical point of view. The problem with this is if you're making a drug, like ibuprofen, for instance, small organic molecule has one asymmetric carbon in it. When you make it, you produce the pair of shoes. You produce a racemic mixture. So when you buy that drug, you buy the racemic mixture. Only one of the two enantiomers is actually a pain reliever. The other one is theoretically useless, but in practice it actually is an antagonist for the correct enantiomer. It takes about 30 minutes for Advil or ibuprofen to produce any effect in your body. And that's largely because of that racemate that's there, as we call it. The pure enantiomer that's active works in about 5 minutes. So why aren't you getting the pure one? It's economics. How much are you willing to pay for one ibuprofen pill? Got a headache, 2 ibuprofen. If it's 10 cents, fine. If it's $10, no, I'll stick with a headache, or I'll use Tylenol or aspirin. So it's how much does it cost to separate that pair of shoes, the racemic mixture? It costs a ton of money because those two enantiomers, those two mirror images, are identical under most of the tools that that we use, like recrystallization, distillation, those are not able to separate enantiomers at all. Gas chromatography, not at all. It's very hard to separate enantiomers. Best if you don't produce them in the first place. And there is a big emphasis on what are called asymmetric reactions that produce a pure or mostly pure enantiomer. Because if you have to separate enantiomers on a large scale, forget it.
So that, is like naturally occurring? Like,
Well, it's the result, inevitable result of that synthesis. You could then try to separate the two, but you'd lose half your material, which is very wasteful from the beginning, and it would cost a lot of time and money to separate those two. Now, if you go to Europe, you can get the pure enantiomer. You can't get the racemic mixture in Europe. Why? Because it's socialized medicine. People don't pay for drugs. So you don't care what it costs. And the company doesn't care what it costs because they're reimbursed by the government. Here, we have all this complicated business of prescription plans that are limited, no prescription plan, donut hole, et cetera. So the drug industry is very sensitive to how much something costs. If it's something for that's like a chemotherapy drug that you have to take, well, okay, it may cost $1,000 a dose, but it gets paid because that's more severe. For a headache, no. You're starting to see and a lot of drugs like Ritalin, albuterol, these are all traditionally sold as racemic mixtures. The side effects almost always come from the wrong enantiomer being in there. You're starting to see them in pure enantiomer form because more people have prescription plans that pay for it, and also the government has been willing to give the drug company an extended patent on the pure enantiomer when the patent for the racemic mixture runs out. A patent runs 17 years, and that prevents anyone else from making that without your permission, and with your permission they'd have to pay you a fee to use it. Once the 17 years are up, then all of these generic drug companies start making it, and it becomes dirt cheap. Like Lipitor just went off patent. That's what they call a blockbuster drug. That makes over $1 billion a year, which if you factor out is a couple of $1 million a day for that one drug. When you lose that patent, my neighbor worked for Pfizer for 30 years. He's now retired, not by choice. That drug costs thousands of jobs all by itself. You can make a lot of money on one particular drug if everybody has to take it forever, which is another factor. Lipitor is something you take all your life. If you get an infection, you have trouble finding an antibiotic that will cure it. Why? Because you take an antibiotic for 3 or 4 days and you're done. Drug company doesn't make any more money. So there's less incentive to develop new antibiotics because the payoff isn't there. A lot of economics that goes into the drug industry. It's not all evil and driven by bean counters, but it is a big factor. So we're starting to see, and understand that a drug to be developed takes at least 10 years. From the time when you first suspect that a compound has some activity by testing in small animals typically, by the time it goes through all the clinical trials, hundreds of millions of dollars and 10, 12 years have been eaten up. And the patent clock starts from day one. So you're only going to get 5 or 6 years of patent protection on a drug. So you have to make a lot of money in a short period of time. Okay, so if you have to assign RNS, the first thing you have to do is notice when you have an asymmetric carbon or a chiral carbon. That's not hard. For an open chain chain compound, you're looking for two different substituents. So does this molecule have any chiral carbons? No. The only one that could be a chiral carbon, well, okay, first of all, a CH3 carbon can never be a chiral carbon for an obvious reason. A CH2 carbon can never be a chiral carbon. So your attention should immediately go to anything other than a CH3 or a CH2, and never to a double bond carbon, never to a triple bond carbon. So they kind of jump out. If you look at this one here, it could have been an asymmetric carbon, except for the fact that there are two identical groups. Any difference at all counts, but no difference is gone. Even just two groups are saying that's it. Now that molecule that I have up here, be careful what you say about mirror images. It does have a mirror image. Everything except the vampire has a mirror image. Okay? So having a mirror image is not a big deal. But for this compound, the mirror image is an exact duplicate. It's not a new molecule. That's the critical difference. Any molecule that is symmetric and not chiral, doesn't have a chiral center, has a mirror image, but it's of no interest to you at all. This is totally irrelevant. So you can find them in open chain compounds pretty easily. Now in a cyclic compound, it's a little harder. If you look at a ring, a cyclic compound, first of all, make sure you get rid of any CH2 or CH3 carbons. Take those out of consideration. The only two carbons that could be asymmetric are this carbon and this carbon. Now, the simplistic definition of a chiral center as a carbon with four different substituents falls apart here. It's actually not a totally bulletproof definition. It's just a handy one that works for open chain asymmetric carbons. If you have an asymmetric carbon or suspect you have one and it's a ring carbon, you have to use a different approach. So, if I'm going to look at this carbon right here, what I do is, first of all, I make sure there are two different groups coming off the ring. If there aren't, forget it. So there's an H and a Cl. But I don't clearly have a third and a fourth substituent to deal with. So the procedure for a ring carbon is you run a precise bisecting plane of symmetry through the suspected asymmetric carbon and perfectly bisecting the ring. Whatever size it is, cut it in half. Then you look at one side of the mirror compared to the other side of the mirror. So imagine that this is a mirror and one side is the reflection of the other. If the two halves are not perfect mirror images, that's an asymmetric carbon and is equivalent to having four different groups. And what this really means is that that plane of symmetry that I tried to draw is a failure. It is not actually a legitimate plane of symmetry. you take bromocyclohexane, the only carbon that could be chiral is that one at 2 o'clock with the H and the Br. So my final check is to draw a plane of symmetry through that carbon, perfectly bisecting what in this case is a 6-membered ring. Now forget the H and the Br. Just look at the ring structure. The two halves are mirror images of each other. So that is not a chiral carbon. This is, and the one I had before up here, that is a chiral carbon. Now, does that finish that molecule in terms of chiral carbon? Actually, there's another one you need to look at. Right here is a carbon with 2 different groups on it. Now, be careful. You have to bisect the ring through that carbon, so that's a different bisection. But you can see that from this mirror right here, the 2 halves are also not matching. So this molecule actually has 2 asymmetric or chiral carbons. What does it mean when you have 2, in this case, different carbons that are both chiral? Well, imagine you get up in the morning, you go in the closet, and you've got a pair of brown shoes and a pair of black shoes. And it's dark, and you're going to pull 2 shoes out. How many different pairs of shoes do you have? 3? Well, you could pull out,
20.
well,
Yeah.
obviously, more than 2 is a possibility, because you get 2 left shoes, you can get 2 right shoes, you can get a left brown and a right black, or vice versa. There are different combinations. There's a simple formula, 2 to the n, where n is the number of chiral carbons. Two to the n is the number of stereoisomers that are possible. So what's the number here? 4. You have 2 chiral centers. 2 squared is 4. If you think about each asymmetric carbon as being capable in its own right of being R or S. And they're 2 different carbons. One has a chlorine, the other has a methyl. So they could both be R, that's 1. They could both be S, that's 2. This one could be R and this one S, or the reverse, 3, 4. There are 4 possible stereoisomers. Again, they could both be R, they could both be S. One could be R and the other S in 2 different ways. 4 stereoisomers. Is there any relationship between those 4? What about the RR and the SS? Does that suggest that they're related in any particular way that we've been talking about? And mirror images, right? The total mirror image of RR is SS. each carbon is going to flip in the mirror from R to S. So the RR is the mirror image of the SS. So this is a pair of enantiomers. And of course, the RS and the SR are the mirror image flips also. So that's another pair, but a different pair of enantiomers. For the top pair, each member of the pair masquerades as the other one most of the time, except in an asymmetric environment, and then their identities get revealed as being different. So they hide their different identities in a symmetric environment, but it's uncovered in an asymmetric environment. So that's a more subtle difference that isn't always there. And the same for the other pair of enantiomers. So this might be your, well, all right. So what about having these two present, RR and RS? Are they mirror images? No. They're stereoisomers, but they're not mirror images. We have a different term for that relationship. They're diastereomers. Enantiomers are really a subclass of diastereomers. Diastereomers are stereoisomers because of the presence of chiral centers, but they're not mirror images. Enantiomers are diastereomers that are related as mirror images. So the definition is somewhat convoluted. Enantiomers are stereoisomers that are related as mirror images. Diastereomers are stereoisomers that are not related as mirror images. Now, chemists are very practical. Why have all of this mumbo-jumbo terminology? It's because there's a big difference between the relationship of diastereomers and the relationship between enantiomers. If two compounds are related as diastereomers, their physical and chemical properties are always different. They're not mirror images.